Hello again, dear participants. Now I kindly invite Professor Ozcan Yazici from Turkey to the presentation. The title of his talk is The Transfinite Diameter of Bernstein Sets. Professor Yazici, you are welcome to present your study, please.
All right, thank you very much. I would like to thank you for the thank the organizers for this nice meeting and giving me chance to talk at the webinar. Let me share this. All right, so this talk will be in several complex variables, and I will talk about transfinite diameter of Bernstein sets. I will explain all this. What's the transfinite diameter and what's the Bernstein sets? All right. Well, let me start with some basic definitions. We define pluripolar sets. These are the sets which are contained in the minus infinity locus of a plurisubharmonic function. Here, plurisubharmonic function, you can think of like these are the functions which with positive Laplacian. Okay. Here is an example of a polar set in one dimension. C, we say polar instead of pluripolar. Any point, any singleton is a pluripolar because you can write the singleton by this set with this function logarithm z minus z naught in modulus. Well, now we will define transfinite diameter. So we take a multi-index alpha j and we define this, we give this monomials with multi-index z to the alpha j. Here z is the coordinate, the usual coordinate in Cn. And you can count the number of monomials of degree s. This is a simple computation. It's a good exercise for any undergraduate. And this is the number of monomials of degree at most s. Here, we will denote this by ms, okay? We will use this later, these numbers. Now we define transfinite diameter. We take arbitrary points, k points, w1 up to wk, and define this one dimensional determinant. This determinant is basically determinant of the matrix given by these monomials and the points ei, wj. And you can easily see that this is a polynomial of degree here given by LMS. You can easily count this number. Then we define Fekete points. So these are the extremal points for this polynomial. Basically, these are the points where our function, our one-dimensional determinant here, takes its maximum, okay, or supremum here. And we call this Fekete points. And using Fekete points, we define here first this ds. ds is basically this determinant to the power 1 over s. And remember, ls here, it was the degree of the polynomial v, okay? And as s goes to infinity, we take the limit, and this limit is called the transfinite diameter. Well, this limit exists always, okay, and this was shown by Zaharyuta in general, and in one dimension it was shown by Fekete. These are some old results. Well, as you realize here, the computation of transfinite diameter is not easy. I mean, explicit formulas are not given in most cases. For unit pole or intervals, you can compute this, but for a little bit more complicated spaces, this is very hard to compute. Instead, we approximate this transfinite diameter. We give some upper lower bounds and so on. An important result here, which says a compact set is polar or pluripolar if and only if its transfinite diameter is 0. What it says basically, the set is very small if its transfinite diameter is 0. Okay. All right. Well, now we define the sets, Bernstein and Markov sets, and later we will connect these two notions, Bernstein sets and Markov sets, and their transfinite diameter. We will talk about this. Well, what's the Bernstein-Markov inequality? This is a well-known inequality which says basically the subnorm of the derivative of any polynomial here is smaller than degree of the polynomial times the subnorm of the polynomial. This was proved in 1889. And we generalize this inequality and define Markov set. We say a compact set here. This inequality, Bernstein-Markov inequality, it holds on a unit disk, and we generalize this inequality and define Markov sets here. We say a compact set is Markov sets if it satisfies the following generalization of this inequality. Here, in this inequality, on the left-hand side, we have d alpha p. This is basically the partial derivative of the polynomial p. Alpha is a multi-index here. And on the right-hand side, we have a similar thing. Here for Bernstein-Markov inequality, we have degree p. We have degree p here as well. Now we take the supremum over a compact set. And there is an extra r here. We will also talk about this. Okay. So if this inequality holds for any polynomial and for some r and for any multi-index alpha, we say our compact set K is a Markov set. Okay. And you can guess easily here, unit disk or ellipsoids. These are all Markov sets. Okay. These are nice sets, but well, when r is equal to 1, we say our Markov set, we call it Bernstein set, okay? So basically, when r is equal to here 1, we say that our compact set is Bernstein. Well, basically, here, any Bernstein set is a Markov set, right? Set of Markov sets is larger. And we have an open problem here. We don't know whether Markov sets are pluripolar or not. We guess that they are not pluripolar. The reason is in one dimension, it was shown that Markov sets are not polar. This is in one dimension in the plane, okay? But in higher dimension, this is open. In 1997, Sicak proved that Bernstein sets are not pluripolar, and this is in any dimension, even in higher dimensions. Bernstein sets are not pluripolar. That means they are not small, okay? So they are not contained in the minus infinity locus of a plurisubharmonic function. Remember the definition of pluripolar. Pluripolar sets are small sets, you can think of like that. This is hard to pronounce. They here, L and M, I will say, in 2002, they give this lower bound for the transfinite diameter. They show that transfinite diameter of any Bernstein set is bigger than or equal 1 over m times 2 to the n minus 1. N is the dimension of Cn here, and here m, remember this m, okay, it comes from the inequality here, this M, okay? So Bernstein set satisfies in this inequality with M, and in that case, we have this lower bound for the transfinite diameter. Well, why this is important? Well, in particular, this shows that transfinite diameter is not zero. And if this is non-zero, we know that Bernstein set K is not pluripolar, okay? Well, that was known by Sıcak, but this gives another proof of that fact. And this may give some hope to show that Markov sets are not pluripolar by finding a lower bound, like in the case of Bernstein sets, but we haven't succeeded this yet. Well, before going to our result, let me mention this briefly, the proof of this result. In this result, L and M, they used a deep result of Zaharyuta, which says that basically you can compute transfinite diameter using a directional Chebyshev constant, and this is a tedious. It has some tedious computations, and it's not easy to employ, but somehow they use that and show this lower bound. And recently we proved this a similar, a little bit better lower bound using a very simple technique. Okay, and we show that transfinite diameter is bigger than 1 over E and M. And in the proof, we use some extremal points other than Fekete points. Remember, in the definition of transfinite diameter, we first find some extremal points, and using these extremal points, we define a limit, and that limit was the transfinite diameter. But now we will introduce other extremal points, and using these extremal points, we will show this result. Let me go over the proof, just a sketch. Before the proof, let me first give this extremal set, how we construct these points for the transfinite diameter. We take an arbitrary point, A1, in the compact set. Let's say W1 is W1 is 1. We construct these extremal points inductively. Let's say we're given this K minus 1 points in the compact set K. Then we define a polynomial PKZ by this kind of Wandermonde determinant. All right, so this is a polynomial in Z, and you can easily see that. Or maybe before we talk about this. All right, so this is a polynomial in Z, and it has supremum at some point, let's say AK. Okay, so we choose AK as the extremal point for this polynomial. All right. Then we construct the sequence of extremal points, and here Jędrzejowski, he showed that using this extremal point, one can compute transfinite diameter, okay, dk. All right. So this is how we construct the extremal point for transfinite diameter. Now we prove our results. Remember, that was the theorem here. Transfinite diameter is bigger than or equal 1 over E and M. N is the dimension, and M is the constant in the Bernstein inequality. All right. So we take some extremal point like in the previous slide, okay, a J minus 1 extremal point for the transfinite diameter. And then we define this polynomial PZ. Here V is the Wandermonde determinant. Let me remind this here. The Wandermonde determinant is this, okay. All right. And define this polynomial. Here the bottom is a constant. and the top is a polynomial in one variable z. Okay, so this is a polynomial in z in one variable. All right. Sorry, z is in k as well. It's not one variable, but it's an n variable. Okay, it's an n variable polynomial. And you can easily see the order of this polynomial is alpha j. This follows from the determinant. Remember, the determinant here is given by this matrix, and this shows that basically it has order alpha j. All right. Well, the derivative of p of order alpha j is alpha j factorial, because the order of p is alpha j, right? And what we do is next recall here Bernstein inequality, which says the alpha order derivative of p is smaller than the subnorm of this, is smaller than right hand side here, but left hand side here we just see that it was alpha j factorial, and this is less than or equal right hand side. Here wj is the supremum of the Wanderman determinant. Remember, that's why we get this. I mean, this inequality follows directly from the top one here. Then we apply this inequality several times, and we obtain that wj is bigger than or equal e and m to the 1 minus lj. Here, lj is the sum of all orders up to j. And we take the power of both sides, 1 over lj. Then we take the limit. After we take the limit, we get on the right hand side 1 over e and m, and we prove our result, right? So in particular, this shows that Bernstein sets are not polypolar, but that was known earlier. It's nothing new, I would say. But this here lower bound is new. It's an improvement of the previous bound given by L and M. All right, that's it. Thank you very much.
I would like to thank Professor Yazici for his valuable presentation. Is there any questions or comments? Okay. It seems there is no question. Thank you again, Professor Yazici, for your contribution.
Thank you very much.